This video will cover training OLS models in R. By the end of this video, you should know how you train OLS models in R and how you specify linear models that include products or functions of features in your models. The R code shown in this video is available on the Learning Management System. It uses the data file dcelectricity.rds. You should download those now if you'd like to follow along. You train OLS models in R using the function lm. It has two required arguments. The first is a formula, which is going to specify the label and the features to be used in the model. And the second is a data argument that specifies the tibble that contains the data that will be used to train the model. The formula component is specific to R. It's a way of writing out equations. The basic form of your formula is going to be the name of a label in your data, then a tilde, and then a model specification. The model is a mathematical expression of features in your model. Let's take a look at some sample data before we start modeling. I'm going to load some sample data and take a look at it. We're going to use some features of R that are built into the Model R package, so I'm going to load that library here as well. The sample data file that I'm loading is dcelectricity.rds. I'll load it and then glimpse it. You can see in the output window, this data file contains 4 variables, a date variable, a high temp variable, a low temp variable, and a demand variable. The temperature variables are the temperature in Washington, D.C. in degrees Celsius, and the demand variable is the demand for electricity in the PJM region. Now that we've seen that data, let's think about how we might construct formula to predict electricity demand. Suppose that I think electricity demand is a linear function of the temperature in Washington, D.C. Mathematically, I might write this out as demand equal to B0, the intercept, plus B1 times the high temperature in Washington, D.C., plus some error. The formula for this linear model would just be demand, the name of the demand variable, a tilde, followed by each feature term. In this case, it's just high temp. The intercept, B0, is automatically included. Let's use this formula to train a linear model. In the code window, I have R code that I can use to train that very simple linear model. I use the lm function to tell R that I'd like to use OLS. The formula is demand as the label and high temp as the only feature. And I'm going to use my electricity data tibble as the data to train the model. I'll train that model, save it to the variable model.1, and then we'll print out the contents to see what's inside. Printing out that model, you can see that it shows you the call that actually generated the model, which is just the lm command that we typed in above, and it shows you the 2 coefficients. These are the b's from the mathematical functions that I showed you before. The intercept is 2,292,127, and the coefficient on high temperature is 4,415. So the mathematical formula used by the modeling tool was demand equals B0 plus B1 times the high temperature in DC plus some prediction error. The mathematical model for predictions, after we trained the model and determined those B0 and B1 parameters, is that demand is equal to 2,292,127 plus 4,415 times the high temperature in Washington, D.C. If I were to ask this model to make predictions, this is the formula that it would use. What's going on here is that lm finds the parameter values, these are B0 and B1, that minimize the mean square error of the prediction model on the data that I've given it. B0 and B1 are what lm calls coefficients, and they're defining the mathematical relationship between electricity demand and the temperature in Washington, D.C. The assumption is it's linear, it has intercept B0, and the slope on the high temperature term is B1. Now that we've determined that formula using the modeling tool, we might actually like to create predictions. You can add predictions to a tibble of data using the add_predictions verb. This verb is part of the Model R package, which provides many handy functions for adding predictions, computing errors, and so on. The way add predictions works is you'll take a tibble of data, you'll pipe it to add predictions. The first argument will be a model that you have trained and saved in a variable. It was model 1 in our R example. The second argument will be the name of a new variable. You'll have to put that in quotation marks. That's going to be used to store the prediction. Let's use add predictions to create a visualization of our model predictions. What we'll do is we'll create a scatter plot with the actual demand on the y-axis and the temperature on the x-axis. And we'll add a second layer that similarly has the model predictions on the y-axis and the temperature on the x-axis. Looking at the code window, first I'm going to create a new column in my data that contains the predictions. I do that using the add predictions verb. I take my electricity data, pipe it to that verb. In the first argument, I give it model.1. which is where we've saved that trained model from LM. And in the second argument, I name the variable that I'd like those predictions to be stored in. I'm just going to call it model.1.pred to remind me that they're predictions. I'll save that back to the elect tibble, and then we'll glimpse it to take a look at the output. As you can see, there's now an additional variable in that elect tibble, which contains the predicted electricity demand from that model we just trained. Now I'd like to create a visualization using both the original data and the predictions. In the first layer, I'm going to draw the high temperature on the x-axis and actual electricity demand on the y-axis. I'll make those dots black. In the second layer, I'd like to draw the high temperature on the x-axis, but the predictions from model 1 on the y-axis. I'll make those dots orange. I'll create that visualization. Taking a look at it, you can see the black dots are the actual relationship between electricity demand and temperature. The orange dots are the predictions from this model. Remember, this is a linear function, predicting electricity demand using just high temperature. So all of these dots fall exactly in a line. That line has a slope of 4,415 and an intercept of 2,292,127, the coefficients that we determined using the LM function. Thinking about that visualization, did our model do a good job of predicting the relationship between temperature and electricity demand? The predictions were a flat line, but the actual relationship seems to be more U-shaped. How could we make our predictions better? One way you might think about doing this is adding an additional term to the model that includes the square of the high temperature. You can actually use the formula to include powers of inputs. So let's think about training a different model where we now have two separate terms, one for the high temperature in Washington, D.C., and an additional term for the high temperature in Washington, D.C. squared. We can write that out in the formula notation using our label demand followed by a tilde, then the first term, the feature high temperature, then we use a plus sign and note the second term, the high temperature squared. We have to put this inside the I function so that R knows that we're trying to square the high temperature. Let's train this model in R and create a new visualization. Looking at the code window, first I'm going to train a new model where I include terms for the high temperature and the high temperature squared. I'm still going to use my electricity data to train the model, and I'll save that trained model in model.2, then we'll print it out to take a look at it. Now you can see in the output, there are three coefficients: the intercept term, the coefficient on high temperature, and the coefficient on high temperature squared. We can visualize these predictions in the exact same way. First, we'll add predictions to our electricity tibble, this time using model2, and we'll save that in a variable called model.2.pred. Now that I've run that, let's create a visualization. This visualization is very similar to the last one, except now, in the second layer, I'm using the predictions from model 2 as opposed to the predictions from model 1. Now when I look at the output visualization, you can see my predictions do much better. They follow a U-shaped path that you would expect if there was some kind of quadratic functional form. You can include other functions of your features inside these models. For example, you could multiply two features by each other, or you could include the exponential of a feature. Formulas are very flexible in R, and your options are basically limitless. For example, you could train an OLS model that looks like this, where I have terms for the high temperature and the high temperature squared, also the low temperature and the low temperature squared. What would that formula look like? Again, we'd start with the label, demand, followed by a tilde. The first term, the feature high temperature, plus the second term, the high temperature squared. Again, we have to put that inside the I function, so R knows to square that feature. Followed by the low temperature feature, followed by the same with the low temperature squared inside the I function. Let's train that model. I'll use the LM function, write out the formula that I had in my slides, my label demand, followed by the tilde, followed by high temperature, the high temperature term squared, the low temperature, and the low temperature term squared. I'll still use my electricity data to train the model, and I'll save that result in model.3. I'm also going to generate predictions. I'll do that using the add predictions verb like I have before. You can look at my output. Now the model has 5 terms, the intercept, and the coefficients on each of the terms that I specified in the formula. Going back to my code, I'll create a visualization with both the actual values and the predicted values against high temperature, just as I have before. This time, I'll use model.3.pred. Looking at the visualization, you can see now it's no longer a smooth curve. That's because the x-axis contains the daily high temperature, but our model contains information on both the high temperature and the low temperature, so all of our predictions won't fall exactly in a line. As one last step of analysis, I might like to actually compare predicted values against the actual values to see how accurate my predictions are. This is a useful way to diagnose how well your predictions are doing. In this visualization here, my first layer is going to be a point geometry. On the x-axis, I'll have the predicted value, and on the y-axis, I'll have the actual value of demand. I'll color those dots black. Then as my next layer, I'm going to draw a straight line using the geom AB line geometry. This line is going to have slope 1 and intercept 0. If my predictions were perfect, every predicted value would have the exact same value as the actual value, and all of the dots from the first layer would show up exactly on that slope 1, intercept 0 line. This gives us a measure of how well our predictions are doing. I'll create that visualization. As you can see, in general, our predictions are around that 45-degree line. There are some differences. Predictions are both above and below the actual values. You'll notice that maybe where the predictions get pretty bad are very far out on the right-hand side of the graph, where the predicted values are very large, sometimes close to 4 million, but the actual values are substantially smaller, around 3 million or 3.5 million. We might take this into account if we were trying to further refine this model.